discussion on this. I might have otherwise just got a question. A gentleman pointed out on the base of the third stage these big silver balls on the inside. What the world are those things came? If you don't think about this, our third stage burned some of its propellant to get us into Earth orbit. And then it stayed in weightlessness in Earth orbit for about 3 hours, so the propellants inside here began to slosh around. Well, you can't have sloshing propellants as you initiate a burn. You've got to pressurize the propellants so that the propellants are all forced in the direction of the nozzle. And the silver balls contain helium, the inert gas, which pressurizes the liquid oxygen, liquid hydrogen, without affecting it chemically in any way, and that allows those engines to then burn. And the third stage is going to burn a second time. It's going to burn for about 6.5 minutes. It's going to propel you out of Earth orbit on a path to the moon. It's going to accelerate you from about 17,500 miles an hour up to almost 25,000 miles an hour, which a student of analytic geometry will be interested to know is hyperbolic speed. Hyperbolic means, in a little simpler terms, Earth escape velocity. You leave Earth so fast that if nothing else intervenes, you will leave the Earth forever. Except that something will intervene, because we will rendezvous with the moon, and that'll slow us down, and that'll provide us the staging place from which to return to the Earth. The point is, it is really fast, leaving Earth. And as you leave Earth on the way to the moon, you're slowing down as you go toward the moon because gravity is working against you. So you don't maintain that speed all the way to the moon. It takes you about 3 days to get to the moon. Which if you say it's 25,000 miles an hour, it will only take you 10 hours, but it takes you 3 days. Now, a little bit of orientation. Everything behind this in the building is launch vehicle. First stage, second stage, third stage. It's all propellant tanks and engines, all designed to get us up to the speeds required to conduct the objectives of the flight. Everything beyond this in the room is spacecraft. In the front, the service module, which we pointed out before, and the command module just beyond it, where the astronauts reside for most of the flight. The only exception being when 2 of them are going to enter the lunar module and head down to the lunar surface. That spacecraft, and then in this wonderful big empty truncated cone here, the lunar module adapter, is where the lunar module would be stored at liftoff. Close examination inside of there will reveal no lunar module. So that's where it would be. They built these steps up here so you can see there's nothing in there. But let's picture the lunar module again. Top part is the ascent stage. That's where you are if you're the pilot, and your docking port is above your head. Bigger descent stage beneath you, and then the 4 legs. So pick that whole thing up and stuff it in there. That's how we're configured at launch. That's how we're configured as we leave Earth orbit. But that's not the configuration that will allow us to enter lunar orbit. We've got basically 2 unconnected spacecraft, and we have to go through a maneuver that connects them. That is called transposition and docking. It happens shortly after we begin our trip to the moon. And what happens is the command and service module at the front push out away, actually separate, move out away, turn around 180 degrees so that the nose, instead of being pointed out, is pointed back in this direction. The 4 quarter panels that constrain the lunar module are jettisoned out to the side, and that exposes what? The docking port that's on the top of the ascent stage of the lunar module. So the nose of the command module then docks with that docking port, and now we've got the ability to move crew and equipment back and forth between the 2 spacecraft. Once that is secure, we jettison the 3rd stage, which will not come tumbling back to Earth, right? Because it's going hyperbolic speed away from Earth. It's leaving Earth forever. And in fact, it is on about the same trajectory we are. And we are going to follow a trajectory that, following Newton's laws, makes this beautiful arced S and goes around behind the moon, and it's a point directly opposite the Earth, behind the moon, where we burn the engine on the service module to slow us down to put us into orbit around the moon. Our 3rd stage will follow us along that path exactly unless we do something. So we take the residual propellants that are in the tank, we vent them to the side, that creates a little bit of a side force, and our trajectories begin to diverge. And the 3rd stage, instead of going behind the moon, will actually impact the front of the moon. And people have asked, why would we crash Saturn V 3rd stages into the moon? And it is the great science demonstration of all time. Every place that astronauts had landed on the moon, they deployed scientific instruments. Among those instruments are seismographs, things that measure earthquakes. we have the ability now to create one. As we have a third stage, we know its mass, we know its velocity, therefore we can compute its kinetic energy. When it hits the moon big time, like a huge artillery shell, creates an impact crater about 150 feet wide, and that event is felt by all of the little seismographs at different points on the moon. And just like on Earth, where you might triangulate to find the epicenter of an earthquake, you triangulate these things, you learn something about the internal core structure of the moon from the various measurements that have come back. So that's why it was done.
Isn't it also space junk?
It is space junk.
But it's preventing space junk. Well, it's space junk, but on the...
Oh, yeah. It's just where do you want the junk to go?
Because otherwise it'd still be going, right?
It would all be in solar orbit if we didn't do that. That's right. And in fact, the third stages from Apollo 8 and Apollo 10 are in solar orbit.
Oh, okay.
Okay. That's true. Now, last point to be made here. We're passing the placards for Apollo 15, 16, 17. 17 was the last flight. 43 years ago now. This would have been the second day of astronauts on the surface of the moon on Apollo 17, 43 years ago, 1972. But the point I'm trying to make on the last three flights is we had the use for the first time of this thing called the lunar rover. And the lunar rover is like this go-kart looking device. There's a picture of it directly opposite me, and some other pictures of it in action, like this go-kart looking device. And the idea is pretty elegant. You want to land on the moon in a big, flat, open field with nothing to make that add any risk. But that's not where you want to pick up the interesting samples. So using Apollo 15 as an example, we select a spot on the moon for a landing called Hadley Rill. And a rill, R-I-L-L-E, is like a deep-cut channel on the surface of the moon. What's it doing there? How did it get there? So those are things that are interesting to the geologist, but you can't land right at the rill. That would be too risky. You land at the big open soccer field about 5 miles from the rill. You drive your rover to the edge of the rill, you pick up your samples, you come back. That's day one. Day two, you drive off in the opposite direction, because about 7 miles in the opposite direction you encounter the base of the lunar Apennine Mountains, which rise about 13,000 feet above the surrounding plateau. Another interesting place. Those are the kind of things we could do on the last 3 of the Apollo flights using the lunar rover. Anyway, I will meet you under the command module, and we'll finish our tour from up there.
Did they stuff the buggy in there too?
They stuffed the buggy on the underside of the lunar module, so that when the lunar module landed, it took the day close to the ground.
This actually come apart, then they flipped around and back in. All of that is not that it was just detached. Like, that was the bottom and that was forward. Whenever you see the pictures from the it just launches off.
So you're the astronaut. This is your home for most of the flight. 11, 12 days, whatever the length of the flight would be. Again, a little bit of orientation for you. The device that almost sticks out of the building does not go to the moon. That is the Launch Escape Tower. So if you're with me talking about the drama of Apollo 12 and Pete Conrad almost initiating the abort on that flight, that would have separated the command module right at that point. That solid rocket fires. Range safety officer blows up the rest of the Saturn V. That's what didn't happen on Apollo 12 or any other flight, fortunately. But this thing is jettisoned 3 minutes into flight because it's no longer of any use after the first stage of flight. So now what you have to picture is a little bit different than what you're actually looking at, and that is the lunar module is going to be against the nose of the command module. So let's do this one more time. Lunar module ascent stage, docking port on the top, descent stage beneath it, legs, so if it's on the lunar surface, it's like that. but against the command module, you have to kind of pick that thing up and put it against the nose, because we know the nose is connected to the top of the ascent stage. So it's service module, command module, ascent stage, descent stage, legs pointed in that direction. We get behind the moon at the engine at the base of the service module fires in retrograde, slows you down to put you in orbit around the moon at a height of about 60 miles. Each orbit around the moon is going to take about 2 hours, just given the nature of the lunar gravity at that altitude. 2 astronauts will exit the command module, and through the docking port, and inside the docking port is the hatch that opens up, kind of like in a submarine, between the parts of the vehicle. So you enter the lunar module. Lunar module separates. Engine that's between the legs of the lunar module, the descent propulsion engine, fires also in retrograde. One major burn to lower the orbit, another burn to arrest your forward progress over the landing site, about 10 minutes there, down to the landing site using that descent engine. It takes about 70 minutes altogether. You make the soft landing on the surface. You get out over the course of a couple of days. If you're the astronaut, you plant your flag, set up your instruments, deploy your lunar rover, drive around in your rover, pick up your rock samples, come back, load everything in, and get ready to come back. Now, as you're coming back, the entire lunar module doesn't lift off the surface, because most of the lunar module, mainly the descent stage and the legs, are just dead weight and serve no purpose. Only the ascent stage is going to return. It has its own propellant tanks, its own engine. That thing fires in posigrade. It takes it about 4 hours to catch up with the command module, which has been in lunar orbit the entire time. They approach rendezvous and dock. Our astronauts will then exit the ascent stage, get back into the command module, and then we jettison the ascent stage and use the little bit of remaining propellant to deorbit it, and it hits the surface of the moon. All that's left now is our command module with the astronauts inside, our service module, which has our propellant tanks and fuel cells and engine and so forth. The engine at the base of the service module has to fire to get us out of lunar orbit, just like it did to get us into lunar orbit, kind of the reverse of that. So it accelerates us out of lunar orbit on a path back to Earth. You pass the point where the Earth's gravity becomes more dominant than the lunar gravity, begin to fall toward Earth, faster and faster, 9.8 meters per second per second. Or for those of you that learned in the English system, 32 feet per second per second. And by the time you get to the atmosphere, that adds up to the fact that you're, again, going about the same 25,000 miles an hour as you were when you left Earth orbit to begin with, which is a fantastic rate of speed to enter the atmosphere. Things that hit the atmosphere at that speed are instantly vaporized by the friction. So when we say shooting stars or meteors, whatever we call those things, that's what's happening, is things entering the atmosphere at fast speed. Probably the most interesting meteor ever would have been the service module, which would have been jettisoned before we entered the atmosphere, separated from the command module, hitting the atmosphere, unable to survive the atmosphere, and burning up in a big display over the western Pacific Ocean. Only the command module with the astronauts inside are going to survive. How does that happen? Well, on the underside of this thing, on the blunt side, we have the heat shield. And we're going to be backing into the atmosphere, heat shield first. And the heat shield is of interesting design. It's called ablative. It will not conduct heat, because if it did, we would fry the astronauts. Instead, the surface of this thing will heat up to a high temperature and then flake away. You're backing in, and all these flakes are building up and flaking away as the heat shield ablates or burns off. And kind of creates this shroud around the vehicle. It's heated up to about 3,000, 3,500 degrees. That lasts for about 5 minutes. And then you begin to slow down to the point where that doesn't become so much of an issue. About 15 minutes later, you're at the point where you can deploy the drogue chute that will point you nose up, and then the main chutes that drop you into the water, hopefully next to an aircraft carrier. Hopefully the carriers remember to bring out a helicopter that day to fix you up out of the water and put you on the deck, take you off to Hawaii for a couple of days of vacation before you continue on back. So anyway, friends, that is the end of a typical Apollo flight, and kind of the official end of the talking part of this tour. Comments about the tour are welcomed by our volunteer staff. Those can be left at the information desk if you so choose. Stick around today as long as you wish in the facility. Ask questions, take pictures, do whatever you want in the building. When you're ready to go back, you march the 363 feet, the length of the rocket, to the other end of the building, and about another 50 feet out to the tram, and it's about 2 minutes back to the main